and this is page number 6. So we will try now to get something called normalization the normalization constant, which is A. We know that the harmonic oscillator equation psi of x is equal to A exponential minus m omega over 2 h bar times x squared. We will try to figure out A. How can we do that? So how can we do that? So the easy way, guys, is to apply what I showed you last time, which is to do the following. So we know that the integration from minus infinity to infinity psi of x star dx, that's equal to 1. This is what do we mean by the normalization. This is called normalization. Normalization. And there is another thing, guys, called expectation value. These are very important. Again, I'm using just wave functions here to simplify everything for you. So if we try to solve this problem, guys, we know that since we don't have a complex number right here, we can write this equation as you can see. So minus infinity to infinity, we have A, we have exponential minus m omega over 2 h bar x squared times A exponential minus m omega over 2 h bar x squared dx is equal to 1. That's great. Now I will multiply these. So what I will have integration from minus infinity to infinity. We have a squared absolute value, and we have exponential 2m, of course we have minus 2m omega over 2 h bar x squared, and that's equal to 1. And then continue working, guys, on this integration. So we'll have integration from minus infinity to infinity, and we have here a squared exponential. We know that this 2 will be cancelled with this 2, so we'll have minus m omega over h bar x squared dx, and that's equal to 1. That's great. Now, guys, this integration will be easy to be solved. Just you need to integrate over the exponential, and I can try to show you how can you do that. So this integration, guys, or I can tell you that there is a table to figure out the solution for this integration. So what we have here, actually, we have a squared integration minus infinity to infinity exponential minus m omega over h bar x squared, and that's equal to 1. So there is a table for this kind of integrations, and they will give you here just the answer. You can work on this integration if you would like. I know that your math background is perfect, and you can do this integration, so I will keep it for you guys. Try to play with this integration. So now I will move to page number 7 and try to finish. So here we will see that a squared, and here we have the integration value, which is actually is equal to square root pi h bar over m omega. So square root pi h bar, and here we have m omega, so that's equal to 1, and that means a squared is equal to square root m omega over pi h bar, because we need to have the reciprocal. So let's see here, it should be yes, so that is correct. Or a is equal to m omega over pi h bar to the power 1/4. So this is the normalization constant. We could manage to figure out the normalization constant, and since we did that, so now we can write the state or the wave function for the harmonic oscillator. So it will be m omega over pi h bar, and here we have 1/4, and here we have the exponential minus m omega over 2 h bar, and here we have x squared. So now you can see that this is A, and you can see that this is C. We could manage to figure out the wave function of the harmonic oscillator using this simple technique, which is using the simple equation, the simple way. Sorry, it's not simple equation, but simple way to solve Schrödinger equation. We just used wave function simply, and just avoided Dirac notations, because Dirac notations can make this problem like a little bit harder to be understood. So that's great. So now what we can do, now we can try to solve some problems based on this topic, which is the harmonic oscillator. So for example, if you try to figure out, so we know how to figure out the probability. Now if you try to figure out the probability density, so what you need to do, guys, so the probability density, for example, let's assume so we know that the probability is a function of x, as you can see. So the probability is a function of x. So for example, here we need to see what is the probability density. We will see that. So what's the probability density here? So to see that, guys, we need to apply the following. So we need to do, so this is the probability rho of x dx, and this is the probability density, and actually it is equal to psi of x squared dx. And if we try to write that down, so what we will have here m omega over pi h bar to the power 1/4, and here we will have exponential m omega, of course, minus over h bar, and here we have x squared dx. We need to have dx right here. And if we try to see the probability when x is equal to 0, so we just need to substitute this x with 0, and we will have the probability density at 0, or at x is equal to 0, is equal to m omega over pi h bar 1/4 dx. So actually this is the probability density, guys, for the ground, for the ground state. So actually what we have here is the probability, but what I figured out here is the probability density. So this is for the ground state. Also, there is another thing that we can study beside the, I will write that down, the probability. Beside the probability density, guys, we can study another thing which is called the expectation value. So what do we mean by the expectation value? So the expectation value can be written like this. So we can have the position x and figure out the expectation value for the position x. How can we do that? How can we do that? So to give the expectation value, guys, for this position using the harmonic oscillator wave functions, so you can do that. So that's equal to integration from minus infinity to infinity psi of x, and here we have the position x as an operator, and here we have x divided by integration from minus infinity to infinity psi of x, and here we have psi of x dx. So this is called the expectation value. Now we know that the wave function or the harmonic oscillator state that I showed you, which is this one right here, is normalized. Since it is normalized, guys, so the whole thing here is equal to 1. The whole denominator here is equal to 1, and we will end up with the expectation value for this position operator is equal to integration from minus infinity to infinity psi of x psi of x, of course star, I'm sorry for that. They are equal. Actually, psi of x is equal to psi star, but let's keep it like this, because sometimes in future you might have, not you might have, but you will have functions that have complex numbers. So that's possible. And having complex numbers, guys, with this complex conjugate, so that can completely change the wave function. So that's great. So this is called the expectation value, and keep that in mind, guys. It is important to know that. This is called the expectation value for this operator x, and sometimes people use hat for the operator, but I'm not gonna use it, just keep it as x. So now, guys, the thing that you need to do, just come here, have those functions written here and the x here, and then integrate. So I will do that for you. So that's equal to integration from minus infinity to infinity, and we have here m omega over pi h bar to the power 1/4 exponential minus m omega over 2 h bar x squared, and here we have x, and here we have m omega over pi h bar 1/4 and exponential minus m omega over 2 h bar x squared dx. This is what we will have, guys. So this is easy and not complicated, and just you need to organize everything here to have 1/4 1/4, so that will give you 1/2 right here. So that's equal to integration again from minus infinity to infinity, and we will have m omega over pi h power, and here we have 1/2. We still have the x right here, which is right here. Here we have exponential minus 1/2, exponential minus 1/2. When we add them, that will give me exponential minus m omega over h power x squared and then dx. And that's equal to, we need to have m omega over pi h power 1/2 outside, and then integrate from minus infinity to infinity x exponential minus m omega over h power x squared dx. Again, we have this integration, guys. Actually, to deal with this integration, sometimes it is easy. You can see that this integral that we have right here is odd. This is odd. This is odd integral, or we can call it, for example, like odd integrand. Odd integrand or odd integral. Since it is odd, so this is 0. So what we can expect here, or what did we find? We found that the expectation value of x is equal to 0. This is very important, guys. You will need that. And we will study that using Dirac notations. But it's a good idea to see that using the wave functions. Okay? So using that, or seeing that using the wave function, yeah, can be helpful. So when we study the Dirac notations, for example, so the story will be different, and yeah, so we'll deal with, for example, like psi 1 x psi 1. So we will study something like this, guys. And also we will study, we did study the A dagger and the creation and annihilation operators. So we'll continue studying that, but using the wave functions that we have right now can be helpful for you to understand the harmonic oscillator problem and how you can solve it using quantum mechanics and just in one dimension. So this is just to simplify everything for you guys. I will try now also to get the expectation value for another important operator. So let's do that. So the expectation value for the momentum operator. So the expectation value for the momentum operator. How can we do that? How can we get the expectation value for the momentum operator? So simply we need to do something like this. P, so that's equal to, you can use here hat. So if you used hat right here, hat means operator. So that's equal to integration from minus infinity to infinity psi of x p and psi of x star dx. So we try to figure out, as you can see right here, we try to figure out the expectation value for the momentum. Just we need to integrate with respect to x, the function here, also the complex conjugate for the function right here, and we need to have the momentum. If you would like to indicate the operator with hat, so that's fine, so you can use hat right here, but I don't prefer to do that. So that is great. So now what we need to do, we need to do the same thing that that we did before. So just integrate So that's equal to integration from minus infinity to infinity, and here we will have m omega over pi h bar. We have here 1/4, and here we have exponential minus m omega over 2 h bar x squared, and here we have p operator, and here we have m omega over pi h bar, and we have 1/4, and exponential minus m omega over 2 h bar x squared dx. But the momentum operator, guys, is equal to something. I don't know if you still remember that. So the momentum operator actually is equal to minus I h bar d over dx. Since we have everything in one dimension, so we can use this complete derivative, d over dx. If we have this as a function of x, y, z, so we need to have this as a partial over partial x, for example. So that's great. And now we can write that down. So the expectation value is equal to minus infinity to infinity, and we will have here m omega over pi h bar, and here we have 1/2 because we have 1/4 here, 1/4 here, and it's a good idea to directly differentiate this. So I will include here the minus I h bar from the momentum operator, and have this part, which is minus m omega over 2 h bar x squared. That's great. And then differentiate this part, guys. When we differentiate this part, so d over dx, when we differentiate this, so that will give me, guys, here minus m omega over 2 h bar, and we will have here 2x, and then we will have exponential minus m omega over 2 h bar x squared dx. That's great. Now, guys, we will have all of these constants out, so we'll have minus I h bar, and we will have m omega over pi h bar. We have 1/2, and here we have minus m omega over 2 h bar right here, and also we have 2 right here, so it will be cancelled with this 2 right here, and we will have integration x minus infinity to infinity, and the exponential this with this, so we'll have m omega over h bar x squared dx. You can see, guys, that you have the same story right here. You have odd integral, and this odd integral, guys, will give you 0. So that will give you 0, and you will see also here, guys, that the expectation value for the momentum is equal to 0.